Hello again. So let's continue to talk about the beam analysis. Let's see. So, by the way, I uploaded all these slides under week number 12. So I created another folder in the Blackboard week by week, so you can easily find out the materials and the link for the videos under each week. So okay, so this is the last slide for the beam analysis and beam design. So I'm going to talk about how we can use this AISC manual. In the previous slide, I showed you the chart, fully plastic, inelastic lateral torsional buckling, and elastic lateral torsional buckling. For fully elastic, the fully plastic, we have Mn is equal to Mp, which is the maximum capacity of the beams. And we can easily find out as Fy times Z, the plastic section modulus. Now, when we are in the elastic lateral torsional buckling, which is really bad situation, so we're not going to go over any example problems for that case. It's pretty similar to the elastic buckling in the previous chapter. And that's the situation when your unsupported length is longer than L sub R, in very rare case. But now, if we are within the inelastic lateral torsional buckling, if your L sub B is larger than L sub P, but less than L sub R, and we have kind of complex equations to find out M sub N. Now, this steel manual will provide some of the pre-calculated quantities so that you can easily get that nominal moment. Okay, so we're going to go over the manual. So I'm going to change the screen to my document camera. Okay, so here I have my Steel Bible. Okay, open up the table 3-2. So we're gonna visit this table 3-1 later when we talk about C sub B value, but that's later. So table 3-2, it's the table for calculating the nominal moment for your beam sections. So we can open any pages for this example. Okay, here we have, let's say, 24 by 62. We have a Z, which is a plastic section modulus. And you may not clearly see this, but these first twos are MP. MPX, X stands for the strong axis, and we're calculating the nominal moment or plastic moment about the strong axis. So MP over omega, which is the plastic nominal moment. So the fully plastic when the L sub B is either 0 or less than L sub P, and this is going to be the maximum value of your plastic moment capacity using ASD, right? Because it is divided by omega factor, is multiplied by phi factor, that's for LRFD. So the first two are M sub P, the maximum moment capacity for both ASD and LRFD. The next ones are MRX over omega, and this is phi times MRX. I'm going to talk about MR in a minute, but that is included in one of that's one of the quantities included in our MN calculation for inelastic lateral torsional buckling case. And here we have BF. It is best friend for us. So BF divided by omega and phi times BF. So I'm going to talk about this BF term in a minute. And we already talked about this L sub P, L sub R. These are all pre-calculated guidelines to divide from plastic to inelastic lateral torsional buckling and inelastic to elastic lateral torsional buckling. And we don't need to worry about this shear calculation. By the way, one thing I'd like to mention is this, using this table 3-2. Table 3-2 is based on the z value. As you can see, all these tables are listed based on the z value from the largest in the front page, and going forward, it is descending order in terms of z. And you can also see that some of the sections are grouped together, and there's a space, and every time after that space, the first one, the top in that group, is in a bolded letter, which means that is going to be the lightest section within that group. So for example, from W24/62 up to W18/71, it has a similar value of z starting from 146 through 153. So they group these together. And the lightest section among these 5 sections is 24/62. As you can see, the second number that is based on the weight, and 62 is the smallest value among these 5 groups. So that's how we can read and how we can use this table 3.3-2. So let me go back to the slide and then talk a little bit about this table and how we can use. So z value is the first one, and I said the table 3-2 is based on the order of those sections are based on zx value. And bold type indicates the lightest member in each group. I already talked about that. Why in the world would we pick a member other than the lightest member? Well, the main reason is because the lightest member means the most economical section, right? Having the similar or the same amount of the capacity. L sub P, L sub R, we already talked about this. L sub P is a limiting laterally unbraced length for yielding. L sub R is a limiting laterally unbraced length for inelastic lateral-torsional buckling. And I mentioned the mysterious term BF. Okay, so again, L sub P, L sub R's, those are the 2 guidelines. This is fully plastic, inelastic lateral-torsional buckling, and elastic lateral-torsional buckling. And by the way, this is the equation. So come on. So this is the equation to calculate nominal moment when we are in the range of inelastic lateral-torsional buckling here, which means our unbraced length is between L sub P and L sub R. Okay? And if L sub B is larger than L sub R, then this is the equation to calculate the nominal moment for elastic lateral-torsional buckling range. And you don't need to worry about this. This is too much, right? And of course, your L sub B is less than L sub P or even 0, then you can easily find out the nominal moment as Z times Fy. All right, so let's go on to the next page. So this is similar to this. The only difference is this C sub B. So let's just forget about C sub B at this moment. We're going to talk about that C sub B factor in a minute, but let's just ignore the C sub B and look at all the expression inside this bracket. Okay, that is MP minus MR times LB minus LP over LR minus LP. I know this is complicated equation, right? So what I'm going to do, I'm going to write down those equations in this on the paper. Okay, all right. So here we have equation. The original equation looks like this. Mn, this is, by the way, inelastic lateral-torsional buckling case. So Mn is equal to originally C sub B times everything else inside of this bracket, which is MP minus MR times the ratio between 2 quantities. One is LB minus LP, the other one is LR minus LP. And close the bracket. And this one, of course, should be less than or equal to MP P. So let me go back to the previous slide here. So this is the equation that I just wrote down in the paper. Mn is equal to C sub B times MP minus MR times this ratio, and that should be less than or equal to MP because MP is this, right? The maximum value of our nominal moment. So whatever you have from this calculation shouldn't be larger than MP, right? That's obvious. Okay, so let me go back to this thing. So what is MP? MP is simply Fy times Z, right? So if your section is determined, your Z value is a constant, and Fy is also another constant, which is coming from the um, what is that? Not section properties. This is material property. Sorry. So that is MP, and MR is also a constant. Okay, and that is listed in the manual. So MP is a constant. MR is also constant. LP, LRs are also constant as long as you pick a section. So the only unknown or the variable in this equation is, what's happening here? Yep, is this L sub B. So this is the only variable. So we can reorganize this equation as this. So I'm gonna just focus on this bracket, all the expression inside of the bracket, MP minus MR times LB minus LP and LR minus LP. LR, by the way, is always larger than LP, right? Because of this chart. Look at this chart, LR and LP, right? LR should be always larger than LP. And those are two constants when you set the section. All right, then, so that's the number in the denominator. Numerator, LP is a constant, LB is a variable, and we are calculating the capacity in the inelastic lateral torsional buckling, which means our L sub B is larger than LP, right? So LB is now larger than LP. And these are all the constants. So I can rearrange this expression as this, MP minus, so I'm gonna take these together, okay? That is gonna be MP minus MR over LR minus LP. The reason that I'm combining these two together is because these are all constants, so we can pre-calculate these in numbers, numerical term, when we select a section. And then the leftover is this, LB minus LP. Again, LP is still a constant, and LB is the only variable. So that is in the slide here. So this is the original form in the bracket. And then we rearranged it as this, as I just wrote it in my paper, MP, and we just combine these two together because we can have it when the section is selected, and the only unknown or the variable in this case is going to be LB. Okay, so we're going to take this term as BF, that's the best friend in our the beam analysis. So let me go back to my paper. Oops. Where is the menu? Okay, so nope. Here we go. Here we go. All right, so we're gonna take this guy as BF. Then our expression is gonna be now MP minus EF times LB minus LP. So when I put it back into this bracket, Now, our original equation now is going to be Mn is equal to Cb times Mp minus Bf times Lb minus Lp. That's it. Okay? And this Mp, Bf, and even Lp, we can have it we can pre-calculate those in a numerical term. Okay? All right, so this is the final expression of Mn. It's kind of a simplified in terms of Bf. When you apply the factor, again, we're going to talk about C sub B in a minute, but C sub B is an additional factor in front of Mn. So we can always multiply by this C sub B factor later on. So after applying the safety factor omega and the phi factor, depending on the methodologies, then it is going to be phi times Mn. So now this is the factored moment, which is phi times Mp minus phi times Bf. So because we multiply by phi in front of Mn, so that will be multiplied by to both Mp and this term as well. And my original slide doesn't have any phi or omega term with this Bf, so I just corrected it. So this is my final expression. Now, let me go back to this table 3-2. For W24 by 62. Okay. So I'm not sure how clearly you can see it, but so here we have a section W24 by 62, and then let me so we can clearly see it for this. I think it's better, right? Here we go. Okay. All right, so let's see. So this is the section that I'm talking about, W24 by 62, corresponding Z value is 153. So if you like to calculate MP, MP is going to be Fy, which is 50 KSI times Z value 153. So you can easily get this MP. And by the way, this MP, the factored MPs are available here. 382 is the MP over omega factor, okay, for ASD, and 574 is the factored MP, the plastic moment, which is going to be the maximum, the nominal moment for this beam, 24 by 62. Now, the Mn in the, let me see, clear, exit, okay. So let me go back to, oops. Clear all drawings. Okay, so let me go back to this equation. Oh, let me go back to the chart. So that's MP here, right? Mn in the inelastic lateral torsional buckling, it is depending on the value of your unbraced length. So that is the variable inside of this equation here, right? So how can we calculate this Mn? Well, we simplify the equation as this. Mn is equal to Mp minus Bf times Lb, the variable, minus Lp. So go back to this slide. So this is Mp used in that equation. Here we have Mr, and then this is Bf. I'm just checking the values only for ASD now. So I'm going to write down the value here, and then LP, and all LR here. And actually, we don't need to have LR anymore because LR is already included in this BF calculation. So let's see, W24 by 62 MP is 382. This is MP over omega. And MR over omega is 229. And then BF over omega is 16.1. And then LP is 4.87. So let's say, okay, let's say we have a BM, and let's say L sub B is equal to LP is 4.87, so let's say it's going to be 10 feet. And what is going to be our factored MN? Now I'm talking about MN over, so MN over omega factor. And that is equal to, let me just skip the C sub B as I said. It is equal to MP over omega minus BF over omega times LB minus LP. And this is the equation from here, right? For AISC, Mn over omega is equal to MP over omega minus BF over omega times LB minus LP. Okay, so MP over omega, from the table it says 382, and this is in kip feet. BF over omega, it was 16.1, okay? And then LB is 10 from the given information, and LP from the table, it is 4.87. Everything is now in kip and feet. So that's how we can find out MN over omega using AISC. And you can do the same thing for LRFT. Just make sure that you copy the number for feet times MP, feet times BF, and the LP should be the same. Okay, so that's how we can calculate the nominal capacity. There's one more, one additional way, and that's sometimes way easier, and which is table 3-10. Okay. Let me pause because I'd like to calculate the capacity. Okay, so before we go on to the table 3-10, I just calculated those number for my short example problem. So here it is. So when I plug in 382 for MP over omega and 16.1 for BF over omega, and LB is 10 and LP is 4.87, then I got 299.4 kip feet as my factored nominal moment of W24 by 62 section with this unbraced length, and using AISC, of course. Okay, so let's talk about table 3-10. Table 3-10 is, by the way, for design problems, okay? And this is very complicated. This is just one of the examples of 3-10 table, and I'm gonna show you how we can use this table. So these are the overlapping graphs and charts of our previous chart, okay? Every section will have this relationship. We have a certain range of the plastic range, inelastic lateral-torsional buckling, and then the elastic lateral-torsional buckling for every section. So when we overlap all possible sections, then the chart looks something like this. So the x-axis is the unbraced length, as we see in the previous chart. This y-axis is the factored moment, either mn over omega or b times mn. And the increments are different. AISC method, we have a 20 kip feet increment for each tick, and LRFT, we have a 30 kip feet increment for each tick. And these are the values of factored moment, LRFT and AISC. So how can we use this table? This is for design problem, by the way. So let's say we already know that our factored, our demand is gonna be, let's say 2,700. kip feet. That's going to be our target demand using ASD. Okay, and of course we have two different calculations for demand. So depending on the methodology, we have a different value, the ranges of the value. So let's say our target demand is 2,700, and we also know the embrace length. Let's say it's going to be 14 feet, for example. So how can we use this table? 2,700 is our target demand using ASD. Did I say 14? Yeah, 14 feet is going to be our unbraced length. So we're going to find out the point based on these two information. So this is the 14 feet, and this is 2,700 target demand. And we're going to choose everything on this side, okay, above this line and right on this vertical line. And here we have two different kinds of lines. One is a solid line, the other one is dotted line. Dotted lines are the ones in the not the lightest section. So I'm going to go back to this chart, table 3-2. Oh, let me see. Okay. Okay, so remember that I mentioned that we have a group, and the top of each group is going to be the bolded one. That is the solid line. Everything else with unbolded sections are dotted line in that table. So let's see. Here we have a different groups, and only the top one is going to be bolded. Same thing here. This is just one of the example. And here we have a solid line. Others are dotted lines, right? So dotted lines means not the lightest section. The solid one is going to be the lightest one. So let me go back to the example that I just showed you. So based on the 14 feet of unbraced length with 2,700 of target demand, this is the overlapping point. And we're going to choose the section above and right. And then the solid one is going to be the lightest section. So we're going to find out the very first solid line within that range, which is I believe this one, which is W40 by 249 or something like that. So that's how we can use this chart and read the table 3-10. And we're going to go over the example problems later on today. So I'm going to show you and use this chart again for the design problem. And let me stop this video here. And then the third one will cover the C sub B value. All right. Okay, that's all. See you later.